Okay, so this is page 186, number 27. The directions were to find the critical numbers and then find the relative extrema, that is the maximums and minimums if they exist, and also find where the function is increasing or decreasing. So you know the drill. Given the function, find the first derivative, okay? And so the derivative here is 1 over 3 times x to the 2/3. And then you find critical numbers. Critical numbers are the magic numbers. It's where all the action happens. So, and you find the critical number by setting the derivative equal to 0, or finding where the derivative is undefined. Okay? So in this case, the function is the derivative is 1 over 3 times x to the 2/3. The only place that's undefined is at 0, and it can never be equal to 0 because it has a 1 on the top, the fraction. If you have a number on the top of a fraction, it can never equal 0. Okay, so this derivative is never equal to 0, but it does have a critical number at x equals 0. So then you make the chart. So you make the chart where you have 0 as the middle. Now their chart looks like this. Okay, we do our chart slightly different. And so it's positive to the left and it's positive to the right. Okay, so that's kind of weird. So it's increasing from negative infinity to positive infinity. Okay, and there are no relative extrema. There's no positive. Yeah.
How do you get that the critical number is x equals 0? How do you...
By the fact that it's undefined, if x were 0, then you get 1 over 0. And 1 over 0 is undefined. So you find essentially this, when you stop and think about it, when you're finding critical numbers, you want to find out when the numerator is equal to 0 and find out when the denominator is equal to 0. That's kind of the shortcut thought. And those are the two places, that's going to find where all your critical numbers are. Okay. So that's the deal there. If you graph it, you see that everything matches up. Okay. The next one was 39. And 39 was a similar direction, okay, where it says find the intervals where it's increasing and decreasing, and then find the critical number. So this is kind of interesting because the function is y equals x divided by 2 plus the cosine of x. Okay, so this is number 39 now. So, same old story. Find the derivative, set it equal to 0, and you end up with x is equal to pi over 6 and 5 pi over 6. Now the original problem restricted our domain, so we could only use the numbers between 0 and 2 pi without including 0 and 2 pi. So at pi over 6 and 5 pi over 6, the sign of x is 1/2. That's where you get 1/2 minus 1/2 minus 1/2 is equal to 0. So you just got to know your unit circle, that at x equals here and here, both of those have a sign of 1/2. Okay. So then you make the chart, pi over 6 here, 5 pi over 6 here, plug in the numbers to the left and to the right. Now that's kind of hard because you look at it and you say, this is how we would normally make our chart. We'd say, and this is what you may have done on here, x and f prime, and you'd say, okay, pi over 6 and 5 pi over 6, those are both where it's 0. And so you say, well, wait a second. I have to pick a number between 0 and pi over 6, so I'd have to pick out something like pi over 12. And you're like, well, Mr. Johnson never taught us how to find the sign of, or the 1 minus the sign of pi over 12. Okay? How can that be? Well, stop and think.
It's important.
you just pick it up and just yell at the person.
Start talking in an accent.
Yeah, I need somebody who knows like German or something. You just pick it up.
Yeah, wait.
Vietnamese. Just start rambling.
So you should say with like, no.
Okay, back to the problem. If you're filling out the chart and you're using trigonometry and you have these critical numbers and you're finding to the left and to the right, you might say, well, how do I know how to do that when I'm not supposed to be able to use a calculator? Well, I'll stop and think, okay? What I'm essentially doing is here's a derivative, okay, and I have to find f prime of pi over 12. Now, I don't need to know the actual value, I just need to know whether it's positive or negative. So stop and think, where's pi over 12? Well, if this was pi over 6, half of that would be where pi over 12 is. Remember, it's in radians. See? So what's the sign of it? Well, the sign of it is something right here. Okay? Now, I doubt that it's 1/4, but it's around 1/4. Okay? It's because of the curvy nature of the sine wave. So, but what you really know is it's 1/2 minus something around 1/4. Therefore, you know the answer is positive. You see? You're using what you know about the sine function, the unit circle, to be able to evaluate that answer without having to know exactly what the answer is. Okay? And the same thing would hold true for all of them. Somewhere between pi over 6 and 5 pi over 6, well, we can pick pi over 2. Okay? That one's an easy one. And we know that if that would be then 1/2 minus 1 if we did it for pi over 2. And so that would be a negative. And then we do the same thing over here. We could do, let's see, if that's 5 pi over 6, I could do like 11 pi over 12. Or just pi. That'd be okay. And or 17 pi over 19. No, okay, fine, whatever. And so that's where we get it. When you subtract, then you get your positive again. Okay. So this tells you this is f prime. The function is increasing, then decreasing, then increasing. Okay. I'll give you a little hint. If you wanted a visual for yourself, you can say to yourself, well, I know the function goes up, then it goes down, then it goes up. Okay, we're describing the slopes. And look at that, kind of gives you the general look of it, which means that there has to be a maximum at pi over 6, and there has to be a minimum at 5 pi over 6. And then that's how you classify all of the results that we come with here. So the first derivative tells you a lot about it. To find the actual maximum, what the actual maximum value is, you see it's a pi plus 6 squared to 3 over 12. All they did was go back to the original function, plug in pi over 6, and computed what the y-coordinate was. Make sense? Okie dokie. All right, we are going to finish the problem that we started yesterday. We were right at the tail end. And so let's do that, and then we're going to use our calculator to test everything. So let me do a quick run through and make sure that we catch up with where we go. My hair's kind of sticking up here. There. so chatty.
I know.
What's a weird sound?
Like if you just sit and listen to everybody talk.
Let's just listen to everybody. And that's when they become.
Does that have a sound?
Yeah, I was gonna say that.
That's my
So like I
recorder.
can hear that?
Go back and look at this one. You'll hear it.
Are you gonna be able to hear me?
Yes.
You just proved that you don't watch the videos. Not really, because how we don't make it. Yeah,
No, this is the recorder right here.
Oh, okay. Let's see. I probably have. I was like, should we practice that?
That's right. This is what it's like in college.
Like it happened.
Fine.
I don't even care.
Okay, help me out. What was the first one? Positive. Well, I won't bother with those. This alternated all the way, right? Okay. And this is where we stopped yesterday, so we're gonna wrap this thing up. So step 4 says. So step 4 is our summary. And sort of like what I just did in the chart there, the chart for the second derivative tells you where the function is concave up or concave down. So you can come along here and you say, oh, the function's concave up here, it's concave down here, concave up here, and concave down here. Because the sign of the second derivative tells you where the function is concave up or concave down. Okay, so let's wrap it up. So we're going to say, first point, f of x, okay, is concave up on, now what are my intervals? So I need this interval and I need this interval. So there's no restriction on the domain, so it's from negative infinity up to and including negative square root of 1/2. It's a bracket because just like increasing and decreasing, you can only be concave up or concave down over an interval. So you have to have a starting point and an ending point. Okay, so that's why this is the ladder. Okay, so you got to finish off with something. And then we go from, what was it, 0? Okay, to positive square root of 1/2. Okay, and the reason why it's concave up is because f double prime is greater than 0. Now, if you wanted to be official, you would say it's f double prime is greater than 0 on the open interval and then state both those intervals again. But you don't need to for the AP exam. You can just say f double prime is greater than 0. Okay, secondly, f of x is concave down on, and now we need those two intervals. So it's going to be a bracket negative square root of 1/2, comma 0, bracket, okay, and positive square root of 1/2 up to infinity. Because f double prime is less than 0. And this tells us about the concavity of the original function, whatever that wacky thing looks like, on all of these intervals. Okay. We're now going to test it using the calculator. So pull out your calculator, and let's see what we got. I'm going to sneak this chair out of here. Okay. What are you jabbering about back there? Okay, clear everything out. All right, type in the original function. Okay. Now I'm going to show you something kind of cool. We're going to use the second derivative first. We're going to validate that we have the correct intervals. So what we're going to do is we're going to find the second derivative using our calculator and graph the second derivative. Okay, so watch this, it's kind of cool. All right, so this is y1. So in y2, we're going to find the derivative of that. So you got to press the math key. And then we're going to do numerical derivative. And so we're going to find the derivative with respect to x of y1. And we're going to find the derivative at all x values. Okay?
I just forgot how to find the y1.
Got it? Okay. Vars. Vars is your friend. Okay? Now, before we forget, let's not graph either one of these. So take that graph off and take that graph off. See that? So I have unselected both of those. So we're not going to graph either one of those. We're only going to graph the second derivative. Okay. Now, do you know what we're going to do for y3? Yeah, we're going to take the derivative of y2. Okay, so go do that. Now that's the only one we're going to graph. Okay, so we are going to graph that one. Now this is going to take a little while probably. So I'm going to do a zoom 6. Zoom 6, it's going to graph. It actually has to do a whole ton of calculations. And the computer, it's actually a very slow computer relatively. And so you can tell it's thinking. And we should start to see some dots or some weird stuff. Okay, did everybody get something like this? All right, we're gonna zoom in. I'm gonna make a little box right here. Okay, I'm gonna do a zoom box because we really only care about whether or not the second derivative is positive or negative and where it is. So hit the zoom key, do a zoom box.
Yes.
Color ones are slow.
Yes. That's all joined together.
Okay, what I'm doing is I'm doing a little box so that we include, so when we see this graph, it should explode this section of it. Okay, so press enter.
I have all three.
You guys still going on the first round?
Oh no, we're on the Zoom box now.
Okay.
I'm going.
You don't have to be slacking with your desk. So you open this last part, take it to the cylinder.
Yeah. It works with my laptop. And then you just sit down and everything.
I don't know, it just went away.
It's still spinning. You see that orange thing up there? And you literally can't do anything. It's just not. My bread almost to make like a chicken or make like a Jimmy like ice flies all the way down. And it's only 8 years.
Are you working on these or I'm
Like,
why?
yeah, my teacher, and I see, I was like,
Yeah.
and then I showed her, she's like, what are you doing? You know, you can turn on the wall if you want to.
Yeah.
Okay, mine's done.
I've,
Part two.
I've done that before.
Yeah, you can make a part two though.
Yeah. Okay. Now what you have in front of you is a graph of the second derivative. Okay? Look back up here. It's the negative 60x to the third plus 30x. Now we could have just put that in there, but it's a lot more fun to let the calculator do that work. This is the graph of negative 60x to the third plus 30x. Okay? It's the second derivative. Now, do you see, look at, the second derivative is equal to 0 at 3 values. Okay? Huh, imagine that. Okay? So, let's find out this value right here. What x value is this? Okay? Go find the 0 using your calculator. So calculate the 0. Oh yeah, the left bound. You know what we should do? I think we should modify the y's so we can see the whole curve. You want to do that?
No.
Yes. No, it's not. All right, well, we won't.
She's calculating. I can't find anything.
Okay.
Got it.
All right. I found my middle point right here. So all you have to do is find this one right here. Go to the right just a bit. And then that can be your left bound. And then you can just go past. There it is. I'm past it. get 0.7071? Okay.
My time is loading.
All right, now just to test it, that's supposed to be the same as the square root of a half. Okay, so I'm going to do a second quit, get out of this, and I'm going to press X. Whoopsie. I'm going to press X. And remember, we found a 0, so that's the value. And so I'm going to do the square root of 0.5. And there they are. Now they start to become inaccurate after that, and that's because it's doing the computations on computations on computations. So we get some inaccuracy there. So we found the correct place. Okay. So this one is good. This one is the negative square root of 1/2. And this one is the 0. Okay. All right. So back to the original graph. Here's how you read this. Second derivative is positive here. It's negative throughout this interval. It's positive here, and it's negative. Therefore, the function y should be concave up, then concave down, concave up, and then concave down. We have validated the chart that we made. Now let's graph the original function and see if it actually is concave where it's supposed to be concave.
When you do the summaries, do you have to write like the points of inflection?
Oh, shoot, we forgot to do that, yes. Yeah, in fact, before I forget, let's do that right now. Yeah. She's totally right. I just simply forgot it. So, step 3, f of x has how many points of inflection? 3. So it has 3 inflection points. At x equals, and then we can identify them here, here, and here. So it's these 3 values. Negative square root of a half, 0, and positive square root of a half. And what's the reason we state that we have inflection points? It's really simple. It's because f double prime changes signs. You do not have to state, well, for this inflection point it went from positive to negative, and then from this one it went from negative to positive. It's not required on the exam. So because of the fact that the concavity changed, that's why we have an inflection point. Very good. Thanks. Okay, let's go back to finish this thing off by graphing the original function and see what this looks like. So now highlight the first graph and unhighlight the other ones. Yeah, let's do a zoom standard, and we're probably going to try to fit this one. All right, I'm going to do a zoom box again. I think I'm going to make my box go about like this. So this is where I'm making my zoom box so we can see the whole function. Okay. Now, this is the graph of f of x, and I see it's concave up until it reaches about somewhere in here. You see that? Somewhere in here, it starts to go concave down until it hits here, and then it goes concave up again till about right here, and then it goes concave down. These x values right here would be the square root of 1/2 and the negative square root of 1/2. Can you see it? I would have sworn, is there a point of inflection finder on this? I almost thought there was at one time. Yeah.
Why don't you get on that? That's next semester.
Yeah. Okay, hey, look at this. If you hit the trace key, and then you enter X, it should remember where the old one was. Oh, it's got 0. Oh, we can plug in, watch this. Hit the trace key, and then enter the square root of 1/2. And my graph is off just a little bit. Here's the actual point of inflection right here. So it goes right up to here as the point of inflection. Does this make sense? Okay, we're trying to draw the connection between doing it analytically, doing it visually, and using the calculator, all of those things combined. Does it make sense? Okay, let me show you one last thing. There's a rule that says you can tell this is a maximum and you can tell this is a minimum at these x values. You can tell it because of the second derivative. Does everybody agree that there's a critical number here and a critical number here? Right? Here's the rule. It's kind of cool. It's called the second derivative test for maximums and minimums. It's in your book. If you take the critical number, which we didn't find, you know, the critical numbers come from the first derivative. If you take the critical number from the first derivative and you plug it into the second derivative, if the answer is negative, it is a minimum. No. Plug it in. And the reason is, stop and think about it. If it's positive, it's a minimum. Why is it the opposite? Tell me what the concavity is here. It's concave up. Second derivative is positive. If you plug the critical number into the second derivative and you get a positive number, then you know it's a minimum. Likewise, if you take the critical number, which comes from the first derivative, and you plug it into the second derivative and you get a negative number, that can tell you automatically that the function has a maximum at that critical number. It's the opposite because of the fact that when the function is concave down, there's a maximum there. And when the function is concave up, then that's when there's a minimum. It's called the second derivative test for max and mins. You don't have to know it, but it actually can come in handy. So, I can do a quick check of this. Just follow. Go till 23, right? The first derivative, I'm looking back there, is negative 15x to the fourth plus 15x squared. I'm going to find the critical numbers. Critical numbers here are 0, 1, and negative 1. If I find f double prime of positive 1, look at the second derivative. What's f double prime of positive 1? It's negative 30. The key is that it's negative. So look at, the critical number here is x equals 1. The answer is a negative. That tells you that not only is it concave down there, that there's a maximum at that point. We can do the same thing for f double prime of negative 1. We would end up with a positive, and that tells you that there's a minimum. And that's the deal. All right, your final assignment for curve sketching that we're going to, where we have new stuff, is due tomorrow then. Page 195, due tomorrow.